All right, guys, so today, 4.2, we are talking about U-substitution, which simply is a way to make doing integrals and antiderivatives easier. Because so far, most of the functions that we've done the integral of, they've been pretty nice functions. It's just been a bunch of little functions added together, or you only have one and it's always exponents. So it's been pretty easy to work backwards. But a problem like this, finding the integral of 2x minus 3 squared dx, the way that we would have done this before without U-substitution is we would have taken the 2x minus 3 squared and we would have written that as 2x minus 3 times 2x minus 3. So you would have ended up with the integral of 4x squared minus 12x plus 9 dx. Because once you FOIL that all out, that's what you end up with. So then when you integrate, you would get this x squared would go up to x cubed. You still have the 4, but now you have to times by a third. And then this x would go up to x squared, and you still have the 12, but you would have to times by a half. And then this 9 would go up to a 9x, and then you would have this plus c. So you end up with 4/3 x cubed minus 6x squared plus 9x plus c as your original f of x, right? With U-substitution, what we do is rather than having to FOIL and distribute and do a lot of this algebra up front, what I'm going to do is I'm going to take this inside piece, the 2x minus 3, and instead of a 2x minus 3, I'm going to call it u. So we're going to say that u equals 2x minus 3 because that means that my integral, instead of 2x minus 3 squared, it's just the integral of u squared. But now I'm using u, so I can't use dx because I don't have x's anymore. But I can take the derivative of this function. The derivative, du, just equals 2 dx. Right? This 2x becomes 2, and I'm taking the derivative, so it's du times the 2, but I have to put the dx because I'm deriving with different variables. Well, I'm trying to replace the dx, so I'm going to solve this for dx. I'm going to divide by 2 over here, and I'm going to write that as 1/2 du equals dx. So instead of this dx, I'm going to plug in my 1/2 du. So this is the integral of u squared times 1/2 times du, which is really nice. The 1/2 goes out in front. 1/2 integral u squared du. Well, I know how to do that. That's just my exponent rule going backwards. So instead of a u squared, it becomes a u cubed. But that means I have to multiply by a third. And this 1/2 in front means I have to multiply by a half. And then this du goes away, and I'm left with a plus c, some constant. So this becomes 1/6 u cubed plus c. Well, I don't want u cubed. I want to get back to my x. So I'm going to go back up here to my 2x minus 3 and plug it in for my u. So 1/6 times 2x minus 3 cubed plus c. Now, if I were to work this all the way out, if I were to simplify this, I'm going to end up right here with this f of x. But look at that f of x, 4/3 x cubed minus 6x squared plus 9x plus c. This one, my new one with U-substitution, looks a lot cleaner than the other one. So basically what we are doing is we are looking at our function, our original function, and we want to, when it gets more complicated, we're looking at the inside of the function at what we can replace with a u. So some examples right here. I've got 1/2x minus 3 squared. First of all, I can bring the 2x minus 3 to the top. But before I do that, well, maybe we should. That's basically, this is the integral of 2x minus 3 to the negative 2 dx. But I really don't want to FOIL that all the way out. So I'm going to say that u is equal to 2x minus 3. U is equal to that inside part, which means that du is equal to 2 dx, which means that when I move this 2 over, 1/2 du is equal to dx. So now I can plug this in for the dx, and I can plug this in for the u, or for the 2x minus 3, and now all I have to integrate is u to the negative 2, and this 1/2 du, I'm going to write it this way a few times, but that 1/2 we can put in front, right? So the integral of u to the negative 2 du. Now I use my simple integral rules. The u to the negative 2 becomes u to the negative 1 because I plus 1, but I've got to multiply by the reciprocal, which happens to be negative 1. But then I also have this 1/2 in front that I have to multiply by, and I have a c at the end. So the long steps, this is negative, this becomes negative 1/2 u to the negative 1 plus c. And I can write that, I can kind of clean that up a little bit. I'm going to put the negative 1 on top, and I'm going to move the u to the negative 1 down on the bottom and just call it u plus c. So negative 1 over 2u plus c, but I don't want u's, I want x's. So I go back to my very beginning, and anywhere there's a u, I'm going to plug in 2x minus 3. So this becomes negative 1 over 2x minus 3 plus c. Oh, don't forget the 2 in front of the u. Whoops. 2 times 2x minus 3. So if this was me on the free response, I would stop right there. If you want to distribute and simplify, you're more than welcome to. You can distribute that too. But for me, free response, I'm going to stop right there. Okay, so let's try this again. Root 2x minus 3. I know that that's actually the integral of 2x minus 3 raised to the half. But I really don't want to raise that to the half. That's going to be a lot of messy algebra. So instead, I'm going to say u is equal to that inside, that 2x minus 3. Oh, don't forget the dx. Which means that du, again, is just equal to 2 dx, which means that 1/2 du is equal to dx. Notice how we're using the same numbers a little bit just to kind of get used to it. You're not always going to replace it with 2x minus 3. That's going to change here in a little bit, but right now that's the example that we're using. So I'm going to plug these in. Instead of 2x minus 3, I'm going to plug in a u. So I'm taking the integral of u to the 1/2. And instead of a dx, I'm going to plug in 1/2 du. And the 1/2 I'm going to put in front. Now I integrate. U to the 1/2 becomes u to the 3/2, which means I need to multiply by 2/3. And I also have this 1/2 in front. I can't forget about. And then don't forget to add c. So this becomes 1/2 times 2/3 becomes 1/3 u to the 3/2 plus c. But I don't want u's in my final answer, so I've got to put the 2x minus 3 back in. So 1/3 2x minus 3 raised to the 3/2 plus c. Now again, if this was me on the free response, I'm going to stop right there. I'm not going to simplify any more than that. You're welcome to. You could put the 2x minus 3 3/2 on top, the 3 on the bottom. You could even make this the square root of 2x minus 3 cubed all over 3. I mean, there's so many different ways to simplify this. But free response, I'm going to end right there. Okay. If you're curious, that 3 could be on the bottom. The 2x minus 3, we could keep that raised to the 3rd, but then change it to a square root instead of a 3/2, and plus c. But again, that looks messy to me, and I'm okay with this answer. So will the AP test. Okay, integral of 1 over cube root 2x minus 3 to the 5th. So we're going to do a lot of rewriting here. First of all, I'm going to rewrite this so you can see the steps. The integral of 1 over 2x minus 3 raised to the 5/3 dx. Remember that you can move this root to the bottom of the 5 as a fraction. But then I want to move it to the top. So this is going to become 2x minus 3 raised to the negative 5/3 dx. I don't want to integrate that. But if u is equal to 2x minus 3, then du is equal to 2 dx, which means 1/2 du is equal to dx. Now I can substitute this and this in, and now I'm just going to take the integral. I know those look like s's sometimes. I'll try really hard not to. The integral of, instead of 2x minus 3 to the negative 5/3, I'm going to put u to the negative 5/3. And instead of dx, I'm going to put the 1/2 in front and the du at the back. So, integrating u to the negative 5/3. I've got to add 1 to that. So that means I'm going to add 3/3, which means this is going to be negative 2/3. But then I have to multiply by the reciprocal, which is negative 3/2. But I also have to multiply by that 1/2 that I had out front. And then add c, because we don't know what the constant is. So 1/2 times negative 3/2 is negative 3/4. And instead of a u, I'm going to go ahead and plug my 2x minus 3 in right now. So 2x minus 3 raised to the negative 2/3 plus c. And again, if I am free responsing, I'm done right there. That looks great to me. If you want to simplify it, you are welcome to. If it was multiple choice, they might want you to put the negative 3 on top and the 4 to the 2x minus 3 to the 2/3 plus c. They might want it that way. Same answer. But this one right here, that looks pretty clean to me. Even on the multiple choice, I'm willing to bet that is going to be the answer quite a few times. Okay. All right, let's do some more. Let's get into some trig functions. Sine of 3x. So this is really the sine of 3x dx. So looking at that 3x is what I'm going to set my u equal to. Because I don't want to deal with trying to undo that chain rule. So I'm going to say that u is equal to 3x, which means that du is equal to 3 dx, which means that 1/3 du is equal to dx. I divided by 3 on both sides to get the 1/3 du. So now when I plug this in and this in, I get 1/3 integral of sine of u du. So the 1/3 goes in the front, the du replaces the dx. Now when I integrate, what derivative takes me to sine of u? Well, that's just the negative cosine of u. And then don't forget that I have this 1/3 out in front that I need to multiply by. So that just becomes negative 1/3 cosine u plus c. And I really don't want the u, so I just replace it back with my 3x. So this U-substitution really is what's helping. We're just undoing the chain rule. That's all this is. We're just undoing the chain rule, which can get really messy if you're trying to do it the long way. So let's do cosine. I like this one. It's going to be a little bit different than what you've seen. We'll go a little bit slower on this example, but I'm taking the integral of cosine cubed of 2x sine of 2x dx. So I'm going to rewrite this first so we can see what's going on. This is really saying cosine of 2x cubed times sine of 2x dx. Now, you might not immediately know what to replace. A lot of people are going to start with, oh, let's make u equal to 2x. But that's not, you can do that. It's just not going to get rid of everything. But if I look at this function, my innermost function is this cosine of 2x because it's inside of an exponent. So I'm actually going to let u equal cosine of 2x, which means that du is going to equal the negative sine of x. Don't forget that you have to times by the 2, the chain rule, and then dx. So that means that du equals negative 2 sine of x dx. Now, before, and this is something you're just going to have to look for with practice. In the past, as soon as we got here to du equals 3 dx, we got dx by itself. But look at our function. We've got cosine of 2x raised to the third, and then I have a sine of 2x dx, which is almost the same as what I have right here, except I have a negative 2. So rather than dividing by negative 2 and the sine of x, I'm just going to divide both sides by negative 2. So that means this is going to be negative 1/2 du is equal to sine of x dx. And the reason I want to do that is because now I can take this negative 1/2 du and plug it in right there because my sine of x dx matches. And obviously this problem was set up on purpose to help you see that this is one way to simplify integrals, right? So I'm going to replace everything. I'm going to replace this. Let's see, what do I got? I got cosine of 2x that I need to replace with u. So I'm going to take the integral of, instead of cosine of 2x, I'm going to put u cubed multiplied by, instead of sine of 2x dx, all I've got to put is negative 1/2 du. And that negative 1/2 I can move to the front. So negative 1/2 of u cubed du. So now when I take the integral, u cubed becomes u to the fourth, which means I need to multiply by a fourth. But I also have that negative 1/2 in the front that I need to multiply by. And the du goes away, and I'm left with a plus c. So negative 1/2 times 1/4 is negative 1/8. And u is actually cosine of 2x. So I'm going to put cosine of 2x raised to the fourth plus c. And if you wanted, that right there is a great answer. You can stop as long as your exponent is on the outside. Some of you like to move it inside, kind of the way the book will usually write when you square or cube or use the fourth power of a trig function. So negative 1/8 cosine 4 of 2x plus c. If you wanted to write it that way, that would be okay. But either one's the right answer as long as you don't goof up when you're trying to simplify. Now, if you, let's say you got to this point right here. You got to here and you thought that this was your answer. If you wanted to check, because that was a pretty messy integral. I mean, that's something that we haven't done before. Instead of solving for dx, we solved for sine of x, sine of 2x dx. If you weren't sure if your answer was correct, to check your answer, all you have to do is take the derivative. So if I were to take the derivative of this answer right here, if I were to take my derivative, I should end up with the function that I started with. If I were to take the derivative, I should end up with cosine cubed of 2x, sine of 2x dx. We're not going to do that right now, but that's where you should end up if you did it correctly, okay? Let's see. I know the video's running a little bit. We've done a lot of examples here, but let's just do one more. We can go over this one in class, but let's go ahead and do it right here. So the integral of x minus 5 root x plus 5 dx. So this is going to be another one where our u might be a little bit difficult to come up with. So I'm going to rewrite this first as the integral of x minus 5 times x plus 5 to the 1/2 dx. I'm going to give you a hint. Your u is almost always whatever is inside your exponent function. You could do u as x minus 5, but x plus 5 is inside with this exponent. So I'm going to make u equal x plus 5, which means that du is going to equal 1 dx, which is kind of cool because that means that du just equals dx. They're the same thing. So when I go to plug that in, look at what's going to happen. I'm going to get the integral x minus 5, and then instead of x plus 5, I get a u to the 1/2, and instead of a dx, I get a du. Now, before I integrate, I have a problem. We don't want x's. We got rid of some of them over here, but we have that x minus 5 still. But what's cool about this is if I go back to my u function, if I go back here, and I say u equals x plus 5, and if I minus 5 from both sides, then u minus 5 is equal to x. So not only did I solve for u, I also have a function for x. And I can take that function and I can plug it in right there for x. So I'm going to rewrite this as the integral, and instead of x minus 5, I'm going to put u minus 5 minus 5 multiplied by u to the 1/2 du. So that just becomes the integral of u minus 10 multiplied by u to the 1/2 du. And I still can't quite integrate yet because I don't want to deal with undoing a product rule, so I'm going to distribute that u to the 1/2. So integral u to the 1 plus a 1/2 becomes u to the 3/2 minus 10 times u to the 1/2 du. Now I can integrate. So this u is going to go up to 5/2, which means I need to times by 2/5 out in front. And this u is going to go up to 3/2, which means I need to times by 2/3. But I also already have this negative 10 in front that I'm going to have to multiply by as well. And, oh, don't forget your plus c. So rewriting this, I'm going to replace the u. I've got to plug in that x plus 5. So when I rewrite, I'm going to plug the x back in for my u. So I'm going to get 2/5, and instead of a u, I'm going to put x plus 5 raised to the 5/2 minus 10 times 2/3, that's negative 20/3. And instead of a u, I'm going to put x plus 5, and I'm going to raise that to the 3/2. And then I'm going to add c. And that is terrible planning by me. Let's rewrite this over here. So my original function is 2/5 x plus 5 to the 5/2 minus 20/3 x plus 5 to the 3/2 plus c. That's going to be my original function, at least as best as we can get it.